This tutorial will be modeling beams and trusses using Abaqus. And the problem that we're going to model looks like this. We have a beam AB that is supported by a 3-member truss at the right-hand side. The beam is 10 feet long, the truss is 4 feet tall and 6 feet wide, and we have pin and roller supports at A, C, and D. We're given the properties of the beam AB. We're told that it has a moment of inertia of 200 inches to the fourth. Young's modulus is 10,000 KSI. And then for the bars in the truss, they all have a cross-sectional area of 0.5 inches squared and Young's modulus of 15,000 KSI. In this problem, we're going to assume that deformations are small and that everything remains linear elastic. So to model this problem, we've probably seen formulations for both truss elements and beam elements. And a frame is basically the combination of the two. And so when you look at the stiffness matrix for a frame element, which could be oriented at some angle theta, then we have terms associated with axial deformation, which is where these EA over L's come from. And then we have terms also associated with bending. And these terms are multiplied by sines and cosines of that angle theta, just depending on whether how the beam is oriented in space. And so even though Abaqus has the capabilities of modeling beam elements and truss elements, what we're going to do is we're going to basically create our truss using these beam elements or these frame elements. And by introducing pinned connections between the members, then we're basically going to turn these frame elements into truss elements. In other words, they will experience no bending because they're pinned at both ends. The other thing that's going to be different in this problem is that in the problem statement, it's kind of like a textbook problem where we don't really know much about the cross-section other than the properties of the moment of inertia and the cross-sectional area. And so what we're going to do is use the generalized cross-section in Abaqus. And this is going to allow us to basically, for the truss elements, we can specify the cross-sectional area. We can make up values for moment of inertia because the members will not experience any bending because they're pinned at both ends. For the beam, similarly, we have the moment of inertia about the major axis. So we have this number here. We can just make up a number for the area. We can make up numbers for moment of inertia about the weak axis or the minor axis. This I12 is the product of inertia, and it's going to be 0 if you have a symmetric cross-section, which is something that we can assume. Again, in this problem, we only have a 2-dimensional problem, so this isn't really going to play any sort of role. And then similarly, the polar moment of inertia for torsion is also defaulted to 0. That's not to say that we couldn't have torsion, but in this problem, we're assuming that there is no torsion. Okay, so we're going to start by creating a standard model. And we're going to have to create a separate part for each of the members in the structure. So we double-click part. This is a 2-dimensional problem, so we're going to model it in a 2-dimensional space. It's deformable, and for the base feature, because these are all line elements, we're going to model it using a wire base feature. And then click continue. And I'm basically just going to draw a line that is 10 feet long. Now I'm going to convert all of my units into inches. So for 10 feet, that would be 120 inches long. And then we're done. Now I didn't name that part, but maybe we would want to go in and rename it for beam so that we don't get confused when we have multiple parts. The next part, we're going to do the diagonal truss member. If we look at the problem here, we're talking about this member here, member BC. Now member BC has the same properties as member BD, so I'm just going to create one part for BC, and then I'm going to create multiple instances of that part, and then I'll have to rotate this member so that it matches member BD. So for the diagonal, it's also base feature wire, and I'm drawing a line from the origin to a point that is 3 feet or 36 inches to the right and 48 inches upwards. So there's our diagonal member. And then the other part we need to create is for the horizontal bar in the truss. And this member is 6 feet in length, so that's 72 inches. And so down here, I'm basically just entering the coordinates for that point. Okay, so we have our 3 parts. Let's go ahead and create the cross-sectional properties for those. Start with the beam. Go to section assignment, select the beam, click done. And then for section, we haven't created any sections yet, so we can go here to this button on the right here, click it, and we can create the section. Now this is where you make the definition of the type of or the state of stress that the member is experiencing. And like I said, we're going to stick with beams. There is an option for truss members, but the problem is that the truss members don't have rotational degrees of freedom, and so when we input our constraints, we're going to run into some problems. So we're going to create these all as beams. I'm just going to call this beam AB. Or actually, I'll just call it beam. And for the profile, again, we don't have any profiles created yet, so we can click this button here. And we're going to choose generalized. And for the beam, if you go back to the problem statement, we're given moment of inertia, but we're not given cross-sectional area, so we can just make up a number for the area. We're also told this is the moment of inertia about the major axis of bending. We can just make up something for the weak axis, because again, this is a 2-dimensional problem, so nothing is bending out of plane. So for the area, I'm just going to put 1. Moment of inertia is 200. We will assume that it's a symmetric section, and we don't care about the moment of inertia in the weak direction, so we'll just put that in as 1. And then we'll click continue. This box pops up that says that we can't use a generalized profile during analysis integration. That's fine. All we have to do is just change this to before analysis. Now we have the ability to enter the material properties directly in here. This integration before analysis is only available when you're doing, linear elastic analysis. If you have any sort of material nonlinear behavior, then you're not going to be able to use this option, and you would have to define the materials over here. But for our case, we can just put the properties in here for Young's modulus, And for the shear modulus, I did not give values for the shear modulus because we're not going to be looking at shear deformations. So I'm just going to put a number in here. And similarly, Poisson's ratio, we're not going to care about because we're going to assume that there's no shear deformations. Okay, so we've assigned our section to the beam. Let's now do the same for the diagonal. And instead of using the beam section, we're going to create a new one. We're going to call it truss. And again, the beam type is the type that we're going to use. We're not going to use truss type. We're going to do the integration before the analysis, and we're going to have to create a new profile for the truss members. This profile is going to be a generalized profile. And here we're going to input the area for the bars, which is 0.5 inches squared. We're not told what moment of inertia is, but it's not going to matter because we're going to end up pinning those members at both ends, so they're not going to experience any bending. So we're just going to put a value of 1 here, 0 here, 1 here. Click OK. Young's modulus for the bar is 15,000. Shear modulus doesn't matter because we're not going to include shear deformations. And we're going to click OK. Now we need to make sure we select the truss to be assigned to our diagonal member. And then we click OK. And then for the horizontal member, we're going to create a section assignment. And we're actually, because this horizontal member has the same cross-sectional properties as the diagonal members, we're just going to use the truss cross-section that we just created. And we'll click OK. Okay, so we've created sections for all 3 of these. There's one more thing that we need to do anytime we're doing a beam analysis. We need to tell Abaqus what is the direction for the 1 and 2 axes, or for the major and minor axes of bending. And so the way that we do that is we go to the part that we're considering. We're going to make sure that we're in the property module for part 1, and we're going to assign beam section orientation. We got to select the regions of the model to be assigned the beam section orientation, which would be this one here. And then basically the default is that the x-axis is strong axis and the y-axis is weak axis. So like we can just hit enter and it draws in our 1 and 2 axes for the cross section and the tangent, and then we can just click OK, and that's fine. We have to do that for all 3 of our parts. So if we go to property module, model 1, let's see, we want to make sure that we're on the diagonal member. So I double clicked on it over here, and then we go to assign beam section orientation, click, hit done, hit enter, and hit enter again. And that assigns the 1 and 2 directions for that particular member. Now let's move to the horizontal member. Assign beam section orientation. Done. Hit enter again, and then we're done. The next thing we need to do is we need to create an assembly So right now these parts are just sitting off here in my toolbox, and I need to put them here and assemble them. So what I'm going to do is I'm going to double click on instances, choose part, beam, and then for instance type, I'm going to keep it as dependent, meaning that we're meshing on the part. Click OK. So our beam has now been placed. We need to create our diagonal member. Click OK. And you can see here is my beam. Here is my diagonal member. So I need to move that so that this point of the diagonal member is touching the right end of the beam. And so the way that I do that is I choose Translate Instance. I select the diagonal member to translate. And then for the starting point, I'm going to start with this point up here. And I'm basically telling it to move this point so that it's touching this point here. And then we click OK. Let's zoom out. Okay, so we have the diagonal, the first diagonal in place. Let's create another instance, the diagonal. Now this one I'm going to have to rotate it so that it's going to fit where it needs to be. So I'm going to choose Rotate Instance, choose that part, click Done. It asks for the point for the center of the rotation, so we're going to rotate it about the origin here. And it asks for the angle of rotation. Now the angle of rotation is an angle about the z-axis, and it would be positive if it was counterclockwise and negative if it's clockwise. And we need to rotate this member in the clockwise direction. We need to rotate it 53 degrees, and then we need to rotate it another 53 degrees. So my total angle of rotation is going to be negative 106. Now I want to minimize rounding error, and so I'm going to include all the decimals that I get from my calculator. So I have 106.260247. And so now I've rotated it at the correct angle, and it asks us if the position is okay, and we say yes, it is. Then we need to move that instance. So we select it. We're going to move it from this point here at the origin to the end of the beam. And we click OK. And again, I'm going to zoom out just a little bit. And then the last thing I need to do is to put that horizontal member in there. Now for this case, when it places it at the origin, it's laying over top of the beam, and so that could be a little bit confusing. So maybe we want to auto offset so that it's somewhere else away from all the stuff that we've already created. And then I'm going to translate. I'm going to move this point here so that it's touching this point here. And then I click OK, because that looks good. Okay, so what we've done so far is we've created instances of these parts in space, but we haven't defined any connection between them. So even though I moved these things around so that they were touching, in reality they're not touching yet in the model. Okay, so I have to impose constraints on the model that are going to tie degrees of freedom together between different parts, so that we get those pin connections between the truss, and we get that pin connection between the beam and the truss. This is a little bit of a tedious step because there's so many constraints that we have to do. But basically, we're going to go down here in our toolbar or our model tree, and we're going to select the constraints. And there are lots of different types of constraints that are available. The one that we're going to be using is a coupling constraint. And basically, we're going to use this to tie degrees of freedom together between different members in the model. Now, when we choose that, it asks us to select the control points. And because we have members that are overlapping, if I were to select this point here, you're going to find out that it's going to ask me, well, do you want to select that point on this member or that point on this member? And so what I find useful is if I go to my modeling tree here and I go to my instances, I can hide these and then I can unhide them. So let's say we want to hide diagonal 1. We right click on it and go to hide. And now it's not in the model or in the viewport at this point in time. Okay. Now I'm still in the middle of creating that constraint. So let's just click this X here. And now it's still asking me for the constraint control point. And now I can select this one. And I know that on the horizontal member, that's going to be the control. For the constraint region type, we're going to choose node region. And now what I need to do is I need to hide the horizontal member, show the diagonal, click X, and then select this point here. Okay, and so what I'm doing is I'm basically tying this point from the horizontal member to the diagonal member. Let me click done. In the edit constraint box, we basically have the option to choose which degrees of freedom we want to tie together. And we don't want to tie rotational degrees of freedom together because otherwise it would be a fixed connection between those two members as opposed to being a pinned connection, which is what our original problem statement tells us. So we click OK. Now we can't see anything, but if we show the horizontal member again, you can see that there's a little circle that appears on the model at this joint here. Okay, so we're going to have to go through and we're going to have to do that process for this joint, and then we'll need another connection between the beam and the top of the truss. Okay, so let's now do this joint here. We're going to hide diagonal 2. We're going to click constraints. It's a coupling constraint. We're going to choose the right end of the horizontal member, choose node region. We're going to show diagonal 2, hide horizontal 1. Click this X here, and then select this point. It's a kinematic coupling constraint. We get rid of the rotation, and then we click OK. Now I'm going to hide the beam, and I'm going to hide diagonal 2. And the constraint that I'm going to create is at the top of the triangle. It's a coupling constraint. The control point is going to be on diagonal 1 at this point. The constraint region type is a node region. And then for the nodes that we're coupling to, we're going to show diagonal 2, hide diagonal 1, click the X, and then select this point right here. And then we click OK. And then the last one that we need to do is between the beam and the truss. So I'm going to create a constraint that is going to couple this point to diagonal 1. And this also, we don't want to tie rotational degrees of freedom. And click OK. Okay, so let's make sure that all of our model is shown here. You can see that we have all of our pin connections between the different members. So that's, now everything's connected. And because we only tied U1 and U2 in these members, it's going to behave like a truss. Next thing we're going to do is we're going to apply our loads and boundary conditions. For the boundary conditions, this is a displacement rotation boundary condition. Up here, we have a pin support, so we're going to restrain U1 and U2. And then at this point, and I'm going to hold in on the Shift key and select this one as well, we're going to restrain U2 and click OK. So now we have the supports as they're given to us in the problem statement. For the loads, we've skipped a step. So right now we just have the initial step in our model. We need to create a load step. So let's cancel out of this and go to steps. Creating a new step, step 1. This is a static general step. Click continue. And we don't need to do anything here. Basically, it's linear elastic and we're ramping everything up over a 1 second period, which is just fine. So we click OK. And now our loads can be applied in the load step, step 1. We have, for the beam, instead of having like a surface pressure or a surface traction, our load is given to us as a line load. And we're going to apply that to the beam. And the force is acting in the downward y direction. So for component 2, we're going to have negative whatever that distributed load is. The distributed load was given to us as 2 kips per foot. I need to convert that to kips per inch. And that gives me 0.1666667. Okay, and again, I'm trying to minimize rounding error. And we'll click OK. One last thing we need to do is to create our mesh and assign our element types. So let's go back up to beam and double click on mesh. First thing we're going to look at is assign element type. We're going to choose our beam. And then we can look at the type of beam elements that are available to us. So we could do linear, quadratic. We'll just keep it as linear. And then we have two types. There's the shear flexible and the cubic formulation. The shear flexible is like your Timoshenko beam, whereas the cubic formulation is your Euler-Bernoulli beam. Okay, so in this case we said we don't care about shear deformations. Let's just do the cubic formulation. And the node, or the element type is the B23 element, which is a 2-node cubic beam in plane. If you wanted to learn more information about this particular element, you can go to the reference guides, or the documentation. And if you go to to find the documentation, you can just do a Google search for Abaqus documentation, and this will come up. The manual that talks about the different element types is the analysis manual. So if we click on that, you can see that we have a section that's called Elements. And the beam elements are what are referred to as structural elements. And so you can see all of the structural elements that they have. And so you can learn more about the truss elements if you do need to use those. We're using beam elements in this case. And so you can see like what the beam element library looks like. You can look at the beam section behavior, what are the assumptions, and so forth. So if you ever have a question about like what a particular element is doing, you can always go here and then you can read the documentation. Okay, so we're using a 2-node cubic beam. Click OK. And we need to seed the part. And I'm just going to use a seed of 12 inches on all 3 of our parts. That's probably more elements than are needed for this particular case because it's just a linear elastic problem, but we'll just go with it. So I seed the part and then I mesh the part, and then I have to click OK. And now the model turns blue, so it has been meshed. So let's now mesh the diagonal. Seed the part. It's going to be 12 inches. Assign element type. And again, we're going to do the cubic formulation. And then we click mesh the part. Yes, and it's blue. Then we go to the horizontal member, double click mesh, seed the part, use a size of 12, assign element type, and we're going to choose cubic formulation, click OK, and then mesh the part. Yes. Okay, so now we're ready to run our analysis. We got to create a job. I'm just going to call it job 1. You might want to call it something different so that you don't overwrite other results. Hit OK. And then under my job, I'm going to submit. Okay, and it's giving me a warning that I didn't assign a beam orientation to some of the members. So let's go back and make sure that we did that correctly. Let's go to the property module. We're on the beam. Assign beam section orientation. Enter, enter. Diagonal. Assign beam section orientation. enter, enter, and then the horizontal, assign beam section orientation, enter, and enter. Okay, let's try that again. So we can monitor the job, and things to look for would be if your analysis doesn't complete, then there's a problem in the model. There are warnings that are written here to this tab. So if you go to this tab, you can see what the warnings are going to be. And in this case, it's just giving us a warning that, because we're using kinematic coupling constraints, if we're constraining a degree of freedom, we can't constrain it in another coupling constraint. Okay, so there's an important ordering to how you constrain nodes if you have multiple degrees of freedom being tied together at a particular point. So you just need to be careful about that. And similarly, any errors that would prevent your model from running would show up here. So we can click dismiss. Go to results, and we can look at the deflected shape. And we can see, does the deflected shape match what we expect? And in this case, this is a problem that can be solved using the method of virtual work. So we can check the analytical solution against the exact solution. And what I found was that the rotation at this particular point here should be on the order of 0.0066. And I can query that by going to XY data, ODB field output, click continue, and then I'm choosing unique nodal, and then I want the rotational displacement at a particular point, and I'm going to select this point here. Now, this is an ambiguous selection because it could be telling me the slope in the beam, but it could also be telling me the slope in this truss member, and it could also be telling me the slope in this truss member. So that's no good. So instead of clicking on the point, we're going to look at the node sets, and we can highlight those sets in the viewport. You'll recall that the connection that I made between the beam and the truss was the last connection that I made. So it's going to be under set 7, and it is going to be the master node. So it's going to be this one here. Okay, so just by my knowledge of how Abaqus names sets, I know that this is the one that's dealing with the beam. Now, if I didn't know that, I could always go into Abaqus and create a set of my own, but we're not going to do that today. So if we just plot that, the plot doesn't matter. I'm more interested in what is this number here. Okay, and so I got 0.00568, which is a little bit smaller than what we had from my analytical solution. But keep in mind that there were some assumptions in my analytical solution that probably simplified the problem a little bit more than what the Abaqus elements were doing. So it's at least, rounding it to the, it's within 10% error, I would say. Okay, so that is kind of a summary of how to do the modeling. You should be able to go through and find like what are the internal forces in the members and things like that, but we're not going to spend time doing that today.